Chapter 6, Triangles. The presentation is structured as follows: 6.1, Introduction; 6.2, Similar Figures; 6.3, Similarity of Triangles; 6.4, Criteria for Similarity of Triangles. Introduction. This chapter will build on your previous knowledge of congruent figures, which have the same shape and size. Here, the focus will be on similar figures, which have the same shape but not necessarily the same size.
Similar figures. Similar figures are defined as two figures that have the same shape, regardless of their size. For example, all circles are similar to each other, as are all squares and all equilateral triangles. An important concept to remember is that all congruent figures are similar, but the reverse is not true. Not all similar figures are congruent.
Conditions for similarity. Two polygons with the same number of sides are considered similar if two conditions are met. Their corresponding angles are equal. Their corresponding sides are in the same ratio, or proportion. The ratio of the corresponding sides in similar figures is known as the scale factor. Understanding similarity. An activity to understand similarity involves placing a lighted bulb above a table and casting a shadow of a quadrilateral object. The resulting shadow is an enlargement of the original quadrilateral and is similar to it. This demonstrates the two key properties of similar polygons. All corresponding angles are equal, and all corresponding sides are in the same ratio. Example of similar quadrilaterals. The two quadrilaterals shown, ABCD and PQRS, are similar because their corresponding angles are equal and the ratio of their corresponding sides is the same. Remark: if a polygon is similar to a second polygon, and the second polygon is similar to a third, then the first polygon is also similar to the third. Similarity of triangles. Two triangles are considered similar if their corresponding angles are equal, their corresponding sides are in the same ratio. Triangles with equal corresponding angles are known as equiangular triangles. Basic proportionality theorem, also known as Thales' theorem. If a line is drawn parallel to one side of a triangle to intersect the other two sides, it divides those two sides proportionally. Activity for basic proportionality theorem. This slide describes an activity to demonstrate the theorem. By drawing a line DE parallel to the side BC of a triangle ABC, it is observed that the ratio of AD to DB is equal to the ratio of AE to EC.
Proof of basic proportionality theorem. Theorem 6.1. If a line is drawn parallel to one side of a triangle to intersect the other two sides in distinct points, the other two sides are divided in the same ratio. Proof. Summary. In a triangle ABC, a line parallel to BC intersects sides AB and AC at points D and E respectively. We need to prove that AD divided by DB equals AE divided by EC. The proof involves calculating the areas of the triangles ADE, BDE, and DEC.
Proof continued. The area of triangle ADE can be expressed in two ways. This leads to the following ratios. The ratio of the area of triangle ADE to the area of triangle BDE is equal to AD divided by DB. Proof conclusion. The ratio of the area of triangle ADE to the area of triangle DEC is equal to AE divided by EC. Triangles BDE and DC are on the same base DE and between the same parallel lines BC and DE, so their areas are equal. Therefore, it follows that AD divided by DB is equal to AE divided by EC. Converse of basic proportionality. Theorem 6.2. If a line divides any two sides of a triangle in the same ratio, then the line is parallel to the third side. This theorem is the converse of Theorem 6.1 and can be proven by assuming the line is not parallel and showing that this leads to a contradiction. Example 1 problem. If a line intersects sides AB and AC of a triangle ABC at points D and E and is parallel to BC, prove that AD divided by AB equals AE divided by AC. Solution: since DE is parallel to BC by Theorem 6.1, we have AD divided by DB equals AE divided by EC. By taking the reciprocal and adding 1 to both sides, the equation becomes AB divided by AD equals AC divided by AE. Taking the reciprocal again gives the desired result. AD divided by AB equals AE divided by AC. Example 2. Trapezium problem. In a trapezium ABCD with AB parallel to DC, a line segment EF is drawn parallel to AB, intersecting the non-parallel sides AD and BC at E and F. show that AE divided by ED equals BF divided by FC. Solution: join a C to intersect EF at point G. In triangle ADC, since EG is parallel to DC, by theorem 6.1, AE divided by ED equals AG divided by GC. Similarly, in triangle CAB, GF is parallel to AB. This leads to the ratio AG divided by GC equals BF divided by FC. Example 2. Conclusion. From the two ratios derived in the previous step, we can conclude that AE divided by ED equals BF divided by FC. Example 3. Isosceles triangle problem. In triangle PQR, it is given that the ratio of PS to SQ equals the ratio of PT to TR, and angle PST equals angle PRQ. Prove that triangle PQR is an isosceles triangle. Solution. Since the sides are divided in the same ratio, by theorem 6.2, the line ST is parallel to QR. Because ST is parallel to QR, the corresponding angles PST and PQR are equal. We are also given that angle PST equals angle PRQ. Therefore, angle PQR must equal angle PRQ. Since two angles of the triangle PQR are equal, the sides opposite them must also be equal. PQ equals PR. This proves that triangle PQR is an isosceles triangle. Criteria for similarity of triangles. Angle, 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 AA. Similarity. Criterion. If the corresponding angles of two triangles are equal, then their corresponding sides are in the same ratio, and the triangles are therefore similar.
Side angle side, SAS, similarity criterion. Side angle side, SAS, similarity criterion. If one angle of a triangle is equal to one angle of another triangle, and the sides that include these angles are in the same ratio, then the two triangles are similar. Side side side, SSS, similarity criterion. Side side side, SSS, similarity criterion. If the corresponding sides of two triangles are proportional, in the same ratio, then the triangles are similar. Symbolic representation of similarity. When expressing the similarity of two triangles symbolically, it is crucial to use the correct correspondence of their vertices. For example, if triangle ABC is similar to triangle DEF, you cannot write it as triangle EDF as the order of the vertices matters. Example 4. Parallel lines in triangles. Problem. If line segment PQ is parallel to RS, prove that triangle POQ is similar to triangle SOR. Solution. Since PQ is parallel to RS, the alternate interior angles are equal. Angle P equals angle S, and angle Q equals angle R. Angle POQ and angle SOR are vertically opposite angles, so they are also equal. Because all three corresponding angles are equal, by the AEOA similarity criterion, triangle POQ is similar to triangle SOR. Example 5. Finding a missing angle problem. Given two triangles ABC and PQR with their side lengths, find the measure of angle P. Solution. First, check the ratios of the corresponding sides of the two triangles. We find that the ratio of AB to RQ, BC to QP, and CA to PR are all equal to 1 divided by 2. Since all corresponding sides are in the same ratio, by the SSS similarity criterion, triangle ABC is similar to triangle RQP. Because the triangles are similar, their corresponding angles are equal. Therefore, angle C is equal to angle P. Using the angle sum property in triangle ABC, angle C is 180 minus 80 minus 60, which is 40 degrees. Therefore, angle P is also 40 degrees. Example 6. SAS similarity problem. Given that OA times OB equals OC times OD, show that angle A equals angle C and angle B equals angle D. Solution. The given relation can be rearranged to form the ratio OA divided by OC equals OD divided by OB. The angles AOD and COB are vertically opposite angles, so they are equal. Based on the equal angle and the proportional sides including that angle, by the SAS similarity criterion, triangle AOD is similar to triangle COB. Since the triangles are similar, their corresponding angles are equal. Therefore, angle A equals angle C, and angle D equals angle B. Example 7. Shadow problem. Problem. A girl who is 90 centimeters tall is walking away from a lamppost that is 3.6 meters high at a speed of 1.2 meters per second. Find the length of her shadow after 4 seconds. Solution. After 4 seconds, the girl has walked a distance of 1.2 meters per second times 4 seconds, which is 4.8 meters from the lamppost. We can form two triangles.
the large triangle formed by the lamppost and the tip of the shadow ABE, and the smaller triangle formed by the girl and the tip of her shadow CDE. These two triangles are similar by the AA similarity criterion because they share a common angle, angle E, and both have a right angle. Example 7. Calculation. Since the triangles ABE and CDE are similar, the ratio of their corresponding sides is equal. The ratio of BE to DE is equal to the ratio of AB to CD. Substituting the known values and converting 90 centimeters to 0.9 meters, we get 4.8 plus x divided by x equals 3.6 divided by 0.9. This simplifies to 4.8 plus x equals 4x. Solving for x, we get 3x equals 4.8, so x equals 1.6 meters. The length of the girl's shadow after 4 seconds is 1.6 meters. Example 8. Medians in similar triangles. Problem. Given that CM and RN are medians of triangle ABC and triangle PQR respectively, and that triangle ABC is similar to triangle PQR, prove 3 relationships involving the medians. Solution. Since triangle ABC is similar to triangle PQR, we know that their corresponding sides are proportional and their corresponding angles are equal. I. Prove that triangle AMC is similar to triangle PNR. This is proven using the SAS similarity criterion by showing that angle A equals angle P, and that the ratio of the sides, including these angles, AM/PN and CA/RP, are equal. Example 8. Continued Typhus. Prove that the ratio CM/RN equals the ratio AB/PQ. From the similarity of triangles AMC and PNR, proven in Part I, we know that CM/RN equals CA/RP. Since the original triangles ABC and PQR are similar, we also know that CA/RP equals AB/PQ. Therefore, by substitution, CM/RN equals AB/PQ. Try. Prove that triangle CMB is similar to triangle RNQ. This is proven using the SSS similarity criterion by showing that the ratios of all 3 corresponding sides, CM over RN, BC over QR, and BM over QN, are equal. Summary. Here are the key points studied in this chapter. Similar figures have the same shape, but not necessarily the same size. All congruent figures are similar, but the reverse is not always true. 2 polygons are similar if their corresponding angles are equal and their corresponding sides are in the same ratio. Basic proportionality theorem. A line drawn parallel to one side of a triangle divides the other 2 sides in the same ratio. Converse of BPT. If a line divides 2 sides of a triangle in the same ratio, it is parallel to the third side. Asimilarity. Criterion. If all corresponding angles of 2 triangles are equal, the triangles are similar. Asimilarity. Criterion. If 2 angles of one triangle are equal to 2 angles of another, the triangles are similar. SSS similarity criterion. If the corresponding sides of 2 triangles are in the same ratio, the triangles are similar. SAS similarity criterion. If one angle of a triangle is equal to one angle of another, and the sides including those angles are proportional, the triangles are similar. A note to the reader. For right-angled triangles, if the hypotenuse and one side of one triangle are proportional to the hypotenuse and one side of another, the triangles are similar. This is referred to as the RHS similarity criterion. Thank you for learning with us.